Hello everyone, and let's start this lecture. In this video lecture, we will be moving ahead to the chapter that we are discussing is electromagnetic induction. And the concept regarding this we have understood. So I will take few examples first, and then we'll moving towards further concepts related to this. So this is an example, and let me read it and solve it. What you can do, you can pause the video and solve and then check your answer solution then after. So it says consider long infinite wire carrying a current which is time varying, is a KT, K is going, K is positive. A circular loop of radius A, resistance R is placed with its center at a distance D apart from the wire, and this D is very large as compared to A, so A is very small as compared to D. Find out the induced current in the loop. So we need to find the induced current in the loop. So solution goes like this. So we will say this is how this can be solved. So first of all, we need to find induced EMF, and this induced EMF is going to be equal to minus d phi by dt. And so first we will go for the flux passing through that loop, that conducting loop, circular loop. And as per the formula, it goes like this: integration B dot dA. B is the magnetic field that is existing at that location, and dA is this area of that loop. Now we have been given this A is very small as compared to D. So we can think of this space is just like a point as compared to this thing. So we can say that the field which is at the center of this loop is same as the field at all the locations. Right? So we can treat this B as a particular value, and A is going to be area which is going to be perpendicular to this board, the direction of that area vector. If this is the current carrying wire, so we know there is going to be a magnetic field existing into the plane of this board. So we can say B and A are parallel, so we will find it as a B into A, that is going to be the magnetic flux passing through the loop. As far as the formula of magnetic flux is concerned, it becomes this. Now we need to place the value of magnetic field, which is current due to current carrying this wire. It goes like mu naught into I divided by twice pi into D. And mu naught is a constant, pi is a constant, D is a constant, I is a time varying, so magnetic field varies. Into area can be written as pi A square because A is the radius. So from here we can find the value of this flux which will pass through the loop. Here I hope you have understood this approximation. Since A is very small, so we are considering this B is same at all the locations. If A is significantly large, then we need to find the B at all the points, then we need to integrate. So this condition has been used, this condition, okay. Anyway, let's proceed further. So it goes like this, mu naught A square divided by constant term which is 2D into I. And can we write this I as KT? So we can write it as a K into T. So that becomes the flux. Now you see this flux is a function of time. That means over the time this flux is going to increase or change. So since it is increasing, then we can think of what is going to happen, and that will be using to find out the direction. Let's try to find magnitude. So when we are trying to find magnitude, so we'll write only positive terms, so d phi by dt for magnitude purpose. So this will become mu naught A square divided by 2D into differentiation of this, so K is a constant which will remain there, T will become 1. So this will become the EMF induced. So what is the induced current? So we will say induced current in the loop is going to be I is equal to the EMF that we have calculated divided by the resistance. And EMF is written over here. So answer becomes like mu naught into K into A square divided by twice D into R. So this becomes the formula for the induced current in that loop. Now we can also find out what the direction is going to be using the Lenz law. So this was your Faraday's law application. Now we can use the Lenz law to find the direction. And since the magnetic field inside, so flux inside is increasing. Flux is going inside and it's increasing. So induced flux must be into. So induced flux must be such that which opposes this. So it must be outwards. So induced magnetic field must come outwards. And if you want outward magnetic field, then you need to have a current in this direction. That means the current has to be in the direction which is called anticlockwise. So we will say this is the induced current magnitude and its direction is anticlockwise. So from here you are able to find both magnitude as well as direction in case of induced current. And this is the induced EMF. Understood? Now let's consider this another example. And it reads like this: a space is divided by the line AD. This is AD line. This line divides the space. And this is the reason 1. This side is the reason 1. This side is the reason 2. Reason 1 is field free. And second has a uniform magnetic field B directed into the paper as shown in the figure. ACD is a circular conducting loop. So we got this a conducting loop, which is this loop, and which is semicircular. And the center is this, and plane of the loop is the plane of the plane. So both are in the same plane. And the loop is now made to rotate with a constant angular velocity omega about the axis passing through the O and perpendicular to the plane of the paper. And that is in clockwise. Everything has been shown in the picture. Effective resistance of the loop is also known to us. We need to find first, obtain the expression for the magnitude of induced current. So we need to find induced current. And then we need to show that the current direction, what the direction of that current is going to be. And then we need to plot this induced EMF over the time as for the 2 periods of rotation. So we need to do these things, right? So solution goes like this. First of all, this is the case at t equal to 0. So what you are going to do, you are going to draw a picture when the time is, let's say, t. So after t time has gone through, also it will be rotated by angle theta, and it will entering into the second part or region. So this portion is in the second region where the magnetic field is existing. And what this theta is going to be equal to? Theta is going to be equal to omega into t, because it's moving with a constant angular velocity, right? So theta we have calculated or got, and this area, if we can find this area into the magnetic field, so we can say what that is going to be the flux. So we will start with the flux. So we can write it like this. Let me use this color. The flux that is going to be equal to integration B dot dA. So it starts with this. Both are having parallel directions. So B into A. B is B. A is the area. B is a uniform, that's a constant. A is the area of that sector which has gone into. So this sector area we need to find out. So that sector area is going to be half r square into theta. Theta is the angle by which it rotates. So this area of any sector which forms angle theta, circular sector, you know that. If theta, we replace this theta by 2 pi, so it's become pi r square. So that's the total area. So that proportionate we have found it out. Now theta can be rewritten as, so it becomes b r square omega t, theta is omega t by 2. Now you see this flux is a function of time. So once again we got the flux as a function of time. So whenever we got it, so we can say induced EMF, writing the magnitude alone. So I'm not writing the minus sign because we are writing the magnitude. So d phi by dt, it will become b r square omega by 2. Good. So that becomes induced EMF on this particular loop. Once is this induced EMF, so the first part can easily be handled. What is that first part? It is talking about induced current. So this induced current expression will be E divided by R. R is resistance. So induced current is going to be equal to B R square omega divided by 2 divided into capital R downside. This capital R is the resistance, small r is the radii. Understood? So this is how first part is over. Now let's go for the second part. You know, for the second part you need to use this Lenz law, and we need to ascertain the direction of current. So as this portion goes into magnetic field region, flux increases. So flux is increasing, and you can see from here the flux is increasing over the time. So you will find, and this field is into, so you would like to have a field outward due to induction. So outward induction field, if you want the field outward due to induction, then how much the current, in what sense the current has to run in. So current must be running in this manner. So since if you run current in this manner, then you'll find the induced flux will be outwards, which will be called up opposing the chain the cause which has created it. So this will be the direction of induced current. Okay. So that's how we can find the direction. And third part, plot the graph between induced EMF and the time of rotation for 2 periods. So for third part C, we can use this figure. Now actually this EMF is, we can write this EMF is minus d5 by dt. So if you calculate this, you are going to get it as a minus br square omega by 2 initially, when this situation is like this. So that means this EMF will be constant and negative, so that's why it's a constant and negative. Once it goes completely, this loop, semicircular loop goes completely inside it, then it will be changing. Momentarily it will be 0, then it will be starting moving like this. So flux will start decreasing, current will change its direction, EMF has to change its direction, so it will become positive. So suddenly it will go to this positive, and having the same value, it will remain the constant for first half of the second half of this rotation. Then it again drop to negative value and will live like this. Then it will repeat itself for the next period. So that's going to be the value. So for 2 period it is asking. So this is up to 1 period, this is up to 2 periods. So it will drop to this. Next time it will follow this, and will keep on doing this. You can keep on plotting for next durations as well. So whenever you need to write this EMF, you write with this proper minus. Here I have used simply magnitude, that's why I dropped this minus sign. And current direction we have decided using the Lenz's law. Okay, so that's another example. Next conceptual point is motional EMF. So what it is and how what the concept it includes. Let's talk about this motional EMF. And motional means related to motion. EMF means EMF. It basically says when we move a conducting wire or rod or any object, then an EMF is induced across that object if there exists a magnetic field. So if I need to explain by using the picture, that will become more impressive. So let's say magnetic field is existing into, and it's a uniform everywhere, and it's constant, let's say. So that this uniform magnetic field that is existing in this space. And let's say we are considering a rod, and that is made up of metal, and this rod is being moved with certain velocity. So this has been given a velocity v, and this is moving in this magnetic field. So there's a magnetic field and there's a rod, that's a metal rod, conducting rod, or any conducting object that is having length. And let's say this is the length L. So this entirely its length. And you are moving with certain velocity in a uniform magnetic field. Then you'll find that there will be charge accumulations, and one end of this rod will get one type of charge, another end will get another type of charge. So there will be basically polarization or charge segregations, hence there will be electric field, hence there will be EMF created. So how that's EMF being created, we are going to talk about. So whatever this EMF is going to come in, this EMF is going to be known as motional EMF, because of the reason it is coming due to motion of this conducting object. Let's try to understand what goes inside. So since this is metal, so metal have a free charge or electrons. So though this is a neutral, that means it does not having any external charge or extra charge. So still it will have electrons inside it. So let's consider any electron that is inside it. So we will be finding as this rod moves, this electron also moves. Whenever this electron moves, charge moves in any magnetic field, then there acts a magnetic force. And how that magnetic force is given by, or we can calculate this force on this electron, is going to be QV cross B formula, or as per this formula. Now V cross B, this is B, this is V. If we do the V cross B, so V cross B is going to be in the direction upwards. So upward direction will be V cross B as per the cross product rule. But you'll find this electron is a negative charge, so force will be acting downwards. So this is a magnetic force that I'm talking about. So just to differentiate it for other forces, I'm writing FB, B for magnetic force. So you'll find this electron will experience a force in the downward direction, and this force is coming because of magnetic field. Now since this electron is a free electron, and if somebody applies a force on free electrons, and this electron can easily move in this material, then this will move, and you will find this electron will move downwards, and it will move downwards and will get accumulated over here. So it will be coming in the negative terminal or this downside terminal, and all the electrons will be located here. Now as electrons are moving here, then you'll find there is a vacancy for negative charges, and where there is a vacancy for negative charges or absence of negative charges we can say, so this absence of negative charge is called positive charge. So you'll find equal positive charge will be accumulating over here. So you can see, or you can say basically that electrons are getting downside and positive charge is accumulating upside. So the amount of negative charge downside is equal to the amount of positive charge upside. Then you see, since these charges have got accumulated, and then these charges will be acting like plus charge and minus charge, and if there are charges located, then there is going to be electric field coming in, and electric field direction is from positive charge to negative charge. Then you'll find there is going to be existence of another field that will appear, and that field is electric field. Now this force was acting on these electrons and trying to bring down all the electrons downside, and we know in metallic rod or conductor there are large number of electrons available. So as these electrons are coming downside, so these charges are becoming larger and larger. Charges are becoming larger, then you'll find this electric field is getting stronger. As this electric field is coming in, then this electric field act on this electron as well, and this this electric field will apply a force, and that force will be given by F is equal to, or this is F of force due to electric field, and let me write as EE for electric field. This force is going to be given by formula Q into E. We already know, right? So since Q is negative, so this force will be opposite to the direction of E. So this force is going to be in the upward direction. Now you will see electron is going to face two forces. One is because of magnetic field, another is because of electric field. Now these two forces together will decide what the electron ultimately is going to settle down, or ultimately what this electron is going to do. As these electrons are coming downside, then you'll find this E is growing, so this force is growing. Now as far as this force is concerned, this is a constant, because V is a given constant, V is a constant, E is a constant, so FB is a constant. So a constant force was pulling them down, and a force was growing up as electrons are going downside. So there will be a moment when this force will become equal to this force. When the two forces become equal, then electron will become now in equilibrium. So the number of electrons that have come down, so whatever the charge has gone accumulated downside or upside, that will become constant. No further electron will go downside to increase this charge, and similarly this charge will also not going to increase. So ultimately there is going to be an equilibrium. So can we write here that at equilibrium something happens? What is happening at equilibrium? So we write at equilibrium we will find net force will become 0. So what is the net force? You will find the net force that is made up of two forces, one because of magnetic field, another because of this electrostatic field. This must be 0, because this is what the equilibrium condition refers to. So from here we will be able to say that this force due to electrostatic is going to be negative of force due to magnetic field. And these formulas we have already listed, so we can put the values of these forces. So using these values of the forces, you will find it becomes Q. I'm writing Q. Q is basically electron, and is going to be E is equal to minus Q V cross B. Then you'll find this Q will get cancelled out, whether it's electron or anything, that hardly going to matter for us. And we will get one important relation. That relation is E is equal to minus V cross B. So this is the formula that's going to be there. That means we will get an electric field that is existing in that conductor. And that electric field is going to cause then potential difference, and there will be a potential difference or EMF. So what the potential difference across these terminals is going to be, we can easily find out, because we have got this E, and this E is a constant or uniform, because this is involving V and B, which are given and constant. So we can say potential difference across two ends of rod, or we can say EMF induced, or we can say motional EMF that is going to come in. So that's what the motional EMF is. So I'm going to write as an EMF. So this EMF is equal to integration, this potential difference, we write integration E dot dl, if you remember, right? Now you'll find this E is a constant, and that can be taken outside. Dot dl, dl integration will lead to this L, and we can write it as this E dot dl, E dot dl, and dl integration will convert into L. Now what this L means, it depends, like which is positive, which is negative, that's up to us. So we are considering, let's say, dl in the upward direction. Now that means dl is also going to require direction, so we can give it as a direction. That means where we are choosing this dl, right? So if we are taking this dl in the upward direction, so for L in the upward direction, so dl for us is going to be in the upward direction. Let me use this another color to show that the dl is in this upward direction. So this is direction of dl, or I'm showing it separately. That means dl is in the direction of L, right? Now if you remember, so EMF used to be, basically there used to be a minus sign as well. So minus from starting point to ending point. Let's say this point we name as M point, this point we are naming as N point. So we are integrating this from N point to M point. Are you getting this? So this is basically Vm, potential of M minus potential of N. That's a potential difference. So if we want to write the potential of M, which is going to be higher potential because it's positively charged, N is going to be negative potential. So this potential is defined as minus E dot dl from N to M. That's what the formula goes, right? And when we integrate from N to M in the upward direction, you will get this is going to be our expression. And this is going to be the case only when we are going to use this as a constant numbers. Now in future you might get that V is changing, B is changing, or direction is changing, so that can be a variable as well. So we can make a proper formula from here. So that proper formula is going to go like this. This is going to be equal to integration from N point to M point, so that you can remember from where to where you want to integrate it. And E definition we can substitute over here. So this E definition is going to be minus V cross B dot dl. Right, so we can say EMF is going to be this much. So from here we can write this EMF formula, which is coming as equal to integration V cross B dot dl. And we are using dl as a vector as well, and we are also trying to say this EMF is basically Vm minus Vn, higher minus lower. So this is going to be the EMF formula, and very important motional EMF formula is this. So motional EMF can always be calculated like this, and this is including a vector product in which three vectors are involved, and ultimately it's called a scalar triple product. And then we need to go for the integration, so we need to use the scalar triple product rule, and we can find this EMF. Some of the rules you must be remembering, like if all the three vectors are in the same plane, so it becomes 0. That means if L vector, V vector and B vector, they are coplanar, then EMF will not be induced. And similarly, if any of the two vectors becomes parallel, then it will not be equal to, then it's going to be again becoming 0. It will not be non-zero. So this is a formula which we can use, and this formula is called motional EMF, right? And this can be simplified. In this particular case, you will find in particular case V cross B will become VB, and whatever this V cross B is coming, you can say that's coming in the upward direction, V cross B, and we need to do this dot with L, so that will become again dot product of same direction vector, cos will become 1, so it will become basically in this case EMF will become V into B into dl integration, which it comes out to be BLV. So we can write it as a EMF induced is equal to BLV if all the three vectors are perpendicular to each other. So this is also a direct formula we can use, and this will be coming when magnetic field, length and velocity, all three are perpendicular to each other. You can see magnetic field is into, which is perpendicular to V as well as dl or L you can call, and this V and L are also perpendicular to each other, and so you can say all three are mutually perpendicular. So we will say this is basically getting battery or EMF in them, and that EMF is of BLV, and this EMF is going to be or this battery is going to be some sort of this. That means this will be positive terminal, this is going to be negative terminal, so that positive charge goes here and negative charge remains there, right? So that's going to be induced EMF or motional EMF. For this there is no circuit needed, and if you connect with the circuit, then you'll find the current will start flowing in from this positive terminal to this negative terminal. So this is very important expression, and this is very general expression for induced or this motional EMF and how it is coming. We talked about this entire mechanism. Let me quickly re-explain. When this conducting material was moving, then the electron was experiencing magnetic force. Because of this formula, then charge segregation bring this electric field, then electrostatic formula, then equilibrium condition, then this equation. So from this is also important formula that will help us to find the electric field because of this magnetic field and charge movement, and then potential difference, and then this formula. Making sense? Okay, so let's take this figure as an example and try to use those concepts which we have learned just now. Let's say that is situation at t equal to 0, and let me explain what the situation is. This is a conducting wire that you can see, and this wire is of length L, which is moving initially with velocity V, so that's the initial velocity. And this says there is a magnetic field B is existing into the paper, and this is a frame, and that frame is basically of conducting material, and there is a resistance R is applied, and this is also conducting material, and this is the conductor that is moving with velocity initially U. And M is the mass of this conducting rod, R is the resistance of this conducting rod. So let me write M is mass and R is resistance of rod, and this rod is conducting rod, and there is a B magnetic field into the paper. T equal to 0 scenario is there. Questions can be so many. So first, let's talk about the first question. It says find. So we need to find all the questions that I'm going to list there. First is motional EMF. Motional EMF that's going to be induced. So how much the motional EMF is going to be induced? And you'll find this motional EMF is going to come because this is a conducting rod is moving with velocity u in this magnetic field. And let's say we are now considering the situation of later time t. So in this later time t, let's say t equal to t, this velocity becomes v. So in general, we are trying to find what this EMF is going to be. So you'll find this EMF induced is going to be BLV. Can we write this directly? E is equal to E for EMF, and this EMF is going to be equal to B magnetic field L into V. How we are able to write? Magnetic field and V are perpendicular to each other, and L, all the three are perpendicular to each other, and we have used the formula we have just understood, right? So that means there is going to be a battery created across it. And this will be positive terminal. We have already talked about this is going to be negative terminal. Exactly same question is, so that's why I'm saying, or how to decide which is going to be positive. You consider an electron, then consider V cross B direction, which is going to be upside. Then you'll find electron will experience a force downside, so electron will accumulate over here. Hence positive charge will be there. So this is how we need to decide which one is going to be positive, which one is going to be negative. So using the mechanism, which will basically indicate that it is going to have a current. Then how the current is going to move? Current is going to move like this. So this is going to be induced current. Second question could be find the current in the circuit. So we can find the current in the circuit. So from here we have found what the induced EMF or motional EMF is going to be. And let's say second is induced current. So what that induced current is going to be? Induced current. So now we can use this current and electricity concept or solving of this this particular circuit. So you'll find the total resistance will be R and this smaller, and EMF is going to be this. So it's going to be basically I is equal to EMF that you applied, and this or induced are equivalent total resistance, and total resistance is going to be small r plus capital R, right? As per the equation, right? And then there can be a further question like find the acceleration of this rod. Acceleration of rod. So after understanding first two questions, let's move this towards third question, and it's trying to connect it with this kinematics and dynamics of portion of this physics. So how to get this acceleration? For that, say we need to get the force. So we need to see whether there is a force acting on this rod. Now this is a slider basically. Rod is a slider which can easily slide on this track. So there's no friction. That's what we are assuming. Then you'll find there's going to be current moving in this, right? So situation is like this. There is let me draw another picture. This is a sliding rod, and it is having a current in it. And that's a current, and its length is given to us, and this is existing in the magnetic field B. So it's like there's a current carrying wire in presence of magnetic field. So whenever there's a current carrying wire in presence of magnetic field, there's a formula. You remember that formula, and that formula was I dl cross B. Remember that formula? And B is uniform. Since B is uniform, so we remember this formula becomes I L cross B. L is the length and B is the magnetic field. Now you see this length is this vector. You can treat like this, right? So this is the length vector, and this is B. So we can say L cross B is going to be a force acting in this direction. So I'm drawing the force with the different colors. So you'll find this force is going to be in this direction, and L is being treated like this. This is L direction. L is going to be in the direction of current, right? You know that. So this is L vector in the direction of current. So from there we found the value of this force. So what exactly this force value will become? Let me write over here. We will say this force will have a magnitude is equal to I L into B into sine theta. Sine theta is sine 90 because L direction and B direction they are at 90 degrees. So force will become equal to this. So that's the force. And what is I? We have already calculated I. So we can say how much the force it is going to experience is going to be I in place of I am going to get this E. Okay, this I can further be simplified by putting the value of this E. So it becomes B L V divided by R plus R. So that's the current. Now we can write the value of current over here. So this will become B square L square V divided by R plus R. So this becomes the formula for force. So you might be asked, what is the acceleration, as you have been asking this particular question. So we can say this force is equal to mass into acceleration. Mass is given to us, so you just divide by mass to get the acceleration. So from here you can connect what is this acceleration is F by M, and it's going to be B square, which is magnetic field, L square, which is the length, V the velocity it is moving by, and M mass, and this equivalent resistance. So this is going to be acceleration, but you will say this is going to be opposite to the direction of velocity because velocity is in this direction. So this is not going to be acceleration, rather it's going to be retardation. So we will say this is going to be retardation or deacceleration. Since it is a retardation or deacceleration, is going to reduce the velocity. If initial velocity is given to us, we can find the velocity at any time t. How can we get the velocity? Because we got to know the acceleration. Now you need to know this is acceleration, and if you are interested in finding further calculations, so you can use this A is equal to dv by dt. Can you use this? And this is a function of v, so you just place this as a function of v and then integrate. So from here you can find the final velocity as well, right? So that means you can connect with this kinematics and dynamics portion. So this type of questions are very popular. So what we are going to do whenever there is a conducting rod moving on any track, so you first find this induced EMF, or which is known as motional EMF, and then go for the solving the electric circuit. So this chapter is electric current and circuit, and then again use this formula of force on the conducting rod or current carrying wire, and because of this force you can find what the acceleration is. Then you can use this acceleration to talk about the kinematics, and then you can find what the energy is dissipated and all that is stuff related to this. Okay, so this was one example which relates this motional EMF. Now this motional EMF that we have talked came because of the translation of that rod. Similarly, if we rotate a rod or any conducting wire, then also there's going to be motional EMF, but that motion will not be translatory, rather that will be rotatory motion. So that we will consider in this next upcoming video. So in this video we had some questions related to this induced EMF in the basic part, as well as some motional EMF. Okay, so make your notes and solve similar questions. Thank you.